Log on, tune in, find out. Another good idea from Cambridge.
Professor Arakawa, who will speak on affine W-algebras and Poisson varieties associated with Kac-Moody vertex.
Thank you very much for the invitation. So I'm going to talk about affine double algebras, which are a characterization of a finite double algebra or premise algebra, which means affine double algebra, a kind of affinization of a finite double algebra. And I'll not explain in detail, but for a finite double algebra, there is an important conjecture of Prime proved by Prime himself and Losef and Ginsburg, which relates primitive ideas of enveloping algebra with finite dimensional representations of finite double algebras. And in my talk, I somewhat try to generalize Prime's conjecture to affine double algebras, and then relate it to a conjecture of Kac-Moody. So let V be a vertex algebra. So we have a so-called state field correspondence. Satisfying certain properties. And so I'll in a minute I'll explain an example, but let me try to define this Poisson algebra. So let's see V be the span of those vectors in V. And let V be a quotient of V by this space. So according to Zhu, this has a natural structure of Poisson algebra. So Poisson, the structure of Poisson algebra is given by the following. So the multiplication is given by -1 product. So here index is the same index as here, and the Poisson structure is given by this way. And vertex algebra is called C2 cofinite if this Poisson algebra is finite dimensional. Some people say this is a technical condition, but actually one can show under certain assumption. For example, so I assume that this is G positively graded and finitely strongly generated. This is the same as this Poisson algebra is a finitely generated as a commutative algebra. And also, maybe I assume that weight zero space is one dimensional. So under this condition, it's V is Shizuku-finite if and only if any element in augmentation ideal of associated graded vertex algebra is nilpotent. So this means Shizuku-finite, this condition is a natural generalization. Shizuku-finite vertex algebra is a natural generalization of finite dimensional algebra. And also, there is a surjection from this Poisson algebra to associate graded algebra of so-called Zuse algebra. So if V is Shizuku-finite, then Zuse algebra is finite dimensional. So it has only finite many simple modules. And it's known that there's one-to-one correspondence between simple V module and simple module over Zuse algebra. So if V is Shizuku-finite, then there's only finite many simple modules over this vertex algebra. So I will be treating somewhat half graded by half integer. So if V is graded by half integer, then this must be a Ramon twisted Zuse algebra. But I'm not going to explain about this. And Shizuku-finite vertex algebra are important because if a vertex algebra is Shizuku-finite and rational, which means its module category is semi-simple, then this vertex algebra corresponds to a rational conformal field theory. And if vertex algebra is Shizuku-finite and not rational, non-rational, those vertex algebra correspond to so-called logarithmic conformal field theory. So in both cases, corresponding physical theory is interesting. But the problem is that it's extremely hard to construct such examples. And not many examples are known. So in my talk, I'm not going to talk about general theory of a Shizuku-finite condition, but I'm interested in these two examples. So first case is our favorite case. So let G be a simple Lie algebra over C, and G hat be affine Kac-Moody algebra associated with G. Where K is the central element. And if K is a complex number, for a complex number, let Vk be the upper K be an induced module induced from one-dimensional representation of this parabolic subalgebra on which this central element acts as multiplication by k, and other elements act trivially. So as a vector space, this is isomorphic to G hat negative. And it is well known that this is a vertex algebra. This is a module of affine Kac-Moody algebra. But at the same time, this has a natural structure of vertex algebra by assigning the field corresponding to x minus 1 g equals to xg, which is x tensor xn g2 minus 8 minus 1, where xn equals to x tensor t. Other fields are determined by this condition. Oops. So in this case, is mic on? Okay, can you hear me? Oh, okay. So in this case, this Poisson algebra is just isomorphic to CG star with usual of Poisson bracket, which I identify with CG. So there's nothing interesting here, but a fact is VK, this vertex algebra is not simple in general. So one can consider its simple quotient. So this is a unique graded simple quotient of VK. So this is irreducible as a G hat module. So this is for the critical level, I just put graded. It's a unique graded simple quotient. So this is usually written as VK, LK, lambda 0. It's a irreducible module with highest weight K, lambda 0. And this is again a vertex algebra, and simple as a vertex algebra. So those Poisson algebra corresponding to this simple vertex algebra is a quotient of this algebra by a certain ideal. So I identify with CG. So it's a certain ideal which gives this algebra. And this is graded and the G invariant. Because G invariant because G acts here and the Poisson ideal of CG. So one can consider its zero set.
Actually, if you break the piece of chocolate, it will not.
Let's see. So as Vk is a zero set of Ik. Okay. And this is invariant conic algebraic set of G or G star. And of course, Vk is C2 cofinite if and only if this variety is 0, and it is known that it happens only when k is a non-negative integer, which means Vk is integrable. Yes. Now I want to explain the second example. So let f be a nilpotent element, and k is a complex number as above, and let w k g f be the affine double algebra associated with G f at level k, which is defined by Kac, Rohan, or Kyoto. I'm not going to explain the definition of this vertex algebra, but this is obtained as a certain zeroth cohomology of certain BRST cohomology. So it's defined as a cohomologically. So it's a zeroth cohomology of certain BRST cohomology from Vk. So this is a certain BRST cohomology depending on and in this case, it is known that in this case, it is known that the Poisson algebra is naturally isomorphic to the coordinate ring of Schrodinger's slice. Where E, H, F is SL2 triple as Poisson algebra. And in fact, it's graded associate vertex algebra is isomorphic to a coordinate ring of jet scheme of Slodry slice. So this is jet scheme or arc space. And again, this is never it's cofinite, but one can consider its simple quotient. So so let W down K G F be the unique simple graded quotient.
But with Poisson bracket comes from the Lie bracket from G.
Yes. WK GF, and one can again consider the corresponding variety, which is subvariety of Slodry slice, which is sister invariant with respect to the natural action of sister on the Slodry slice. So this is it's cofinite if and only if this variety consists of only one point, which is a unique fixed point with respect to the sister action. Now the merit of so there's maybe some other way to define double algebra, but the most important consequence of this definition is that one has is that this definition is functorial. This means one has a functor from certain category of modulo of affine algebra to the category of modulo of affine double algebra. So let OK be BGG category of G hat at level K. So I remarked that unlike the finite dimensional case, an object here is not necessarily finitely generated, but still have a nice problem. So by considering the same cohomology, I didn't define this cohomology, but by considering the same cohomology with coefficient in M, this defines a functor from category OK to the category of modulo of WKGF. And we want to understand double algebra or their representation by this through this functor. So because this is BRST cohomology, the cohomology degree it can be both positive or negative, but one can show that this cohomology is 0 for any object of OK. So this means H0 is right exact. But in general, it's not exact for this category. if we consider the minimal nilpotent element, so theta is the highest root. So this is a minimal nilpotent. Then the cohomology. So cohomology is 0 for any objects here, and so this means H. This functor is exact. And image of simple module is 0 or simple. And moreover, any simple module can be obtained in this way. So this was proved by myself, and this in particular means so the BRST cohomology determines character of each irreducible representations of WK. If theta, if K is not critical, because so because of the vanishing, the cohomology can be computed through Euler-Poincare principle, and the character of irreducible representative of G hat is known if the level is not critical. And for other important vanishing does not hold in general, but so if F is a principal nilpotent element, Frankel, Katsuba, Kyoto defined a modified functor, which again I don't explain, but which is called minus reduction functor. With which has nicer properties, and in fact one can prove the same properties as here. So such that the vanishing hold and image of irreducible representation is 0 or simple, and any representation can be obtained in this way. So this again determines each character of double algebra corresponding to the principal nilpotent element, and has the same result if F admits good even grading, then a similar statement holds. So in this case, then there exists a modified functor from certain parabolic category, subcategory of OK to, in general, Raman twisted. Representations with vanishing properties. And reducibility is a difficult problem, and I can only show that it sends simple module to 0 or almost simple module. But for type A, it's almost simple module is always actually simple, thanks to the result of Brandon-Keshev. So this gives a character of each irreducible representation of 4 if G equals to SLN. But for so type A, any element admits a good even grading, but this is not always the case for other types. So I think it's open problem to determine the character of irreducible representation in general. But this functor is nice. This modified functor is nice for deriving these kind of characters, but it only talks about represent. So this functor is a functor from the category OK to the category of a module of W upper K. So this doesn't say anything about the representations of a simple vertex algebra. And today I want to I'm interested in the simple quotient of W upper K GF, which is W sub K GF. So I will stick to the original V-heuristic homology, which defines vertex W-algebra itself. So for this category, I consider smaller, for this purpose, I consider a smaller category than category O. So let KLK be the module of a full subcategory which consists of which is integrable over this finite dimensional D algebra, which means this is a direct sum of finite dimensional representations of G. And of course, V upper K or Vk is objects of this category. And yeah. So the first theorem is the following. So let K be any complex number and F be any nilpotent element. So if F is 0, this means we don't do nothing, so it's an empty statement. So first for the cohomology vanishing holes for any objects here. Secondly, the variety associated with H0 f Vk. So this is, so we have a surjection from here to here, so which induces a surjection from here to here. And this is by definition double upper K GF. So this is a quotient of this vertex algebra, and it's naturally a vertex algebra as a quotient of vertex algebra. So this is a quotient of this vertex algebra. And the simple quotient is, in general, it's a quotient of this vertex algebra. So I can consider corresponding variety. And this is intersection with a variety of Vk with Slodley slices. So this means, in particular, if this so if this happens if this is, so this is if H is 0, if Vk is not 0. So if Vk is not 0, then this must contain corresponding orbit.
Excuse me, and what is the filtration of Vk?
Sorry?
So you're taking associated of Vk. What is the filtration?
So I don't, what?
You have associated of Vk. Yes?
It's a variety. This is max of Vk. So this is this is Vk divided by C2 Vk. Okay. So this is an analog of the corresponding result of a finite double algebra. But so difference between a fine case and finite dimensional case is that this variety is not necessarily contained in the Newcomb. But if this is 0 or C2 cofinite, then corresponding varieties contained in Newcomb. So from this follows from second and third assumption, but if so, the following is equivalent. So W H 0F Vk is non-zero and C2 cofinite. If and only if variety of Vk is included in Nilcomb and corresponding nilpotent element is maximal or open in this variety.
An orbit of what is dense, an orbit of maximum dimension. Maximum, what do you mean by maximum?
It's open. Oh, maximally with respect to the closure. let me say a few words about this. So first, let me consider the case the level is not positive rational. So HX is the Coxeter number. So in this case, H0 of f k is always non-zero and simple. But so if k plus hx is not zero or positive rational, then v upper k is with sub v down k. So the k is already irreducible. So this means wk df is already irreducible. So this never be a physical finite. So the only non-trivial case is a critical level case. So for the critical level, it is known by Frankel and Gasguri that the as Vk is exactly Nilcon. So this means corresponding. So if k is minus hk. So critical level case. So corresponding variety of double algebra is intersection with n and s. And actually, it is known that associated graded vertex algebra itself is exactly the coordinate ring of Z scheme of Nilcon by this is a result of Frankel. That's great. And from this one can show that the associated graded vertex algebra as a critical level is isomorphic to the coordinate ring of this Z scheme corresponding to this scheme. This means W minus hx gf is C2 cofinite if and only if f is principal nilpotent element. And in this case, unfortunately, from this one can see that the corresponding vertex algebra is trivial. Just one dimensional vector space. Finally, I'm going to explain the most interesting case. So let me consider the case k plus hx is a positive rational. And I'm in particular interested in the case of principal admissible representation. So let Vk be principal admissible. So admissible representations are those representations whose characters have a modular invariance property. I will not explain in detail, but for a vacuum to be a principal admissible, K must belong to certain set here. So Q is a natural number which is mutually prime to this is a Lacing number, and PQ is minus H check plus P over Q, where P is an integer which is prime to Q and greater than dual Coxeter number. So if the denominator Q is 1, then this is just a set of non-negative integers. So in this case, just an integral representation. But there are other many interesting cases. And so the corollary of first assertion of theorem 1, which is the variation of cohomology. So this is stated in the paper of Frankie Katz Wakimoto, that so if F is a principal nilpotent element, then this is not a 0 if and only if. So I take K to be from this set where Q is prime to the Lacing number. So this is not 0 if and only if Q is greater than Coxeter number. But corollary of this corollary is that this is 0 if Q is smaller than H. And according to the theorem number 3, in this case, corresponding varieties included in Nilsson. So if K is a principal number with denominator smaller than H, then associated variety is contained in, strictly contained in Nilsson, because it's 0 for principal nilpotent. So in particular, this means so in this case, this is for principal admissible representation whose denominator are smaller than Q are sometimes called degenerate a principal admissible representation. So if Vk is a degenerate principal admissible representation, then the associated variety is containing nilcon. So one can find at least one important element whose orbit is open here. So this means each degenerate principal admissible represent create at least one Shizuko-finite double algebra. So finally, I claim that this variety has a simple description, at least for classical G. So let G be classical, and K belong to this set. Then state means that the corresponding varieties consist of elements add x to q equals to 0. And which turns out to be irreducible. So this means a corresponding double algebra is Shizuko-finite. And if you look at so for type A, this partition is partition of this kind. So this is this corresponds to exceptional double algebra defined by Kac-Moody, and so in particular, this if you look at these partitions in particular, or non-principal exceptional double algebra for G are Shizuko-finite. So exceptional I don't have I'm not going to define exceptional double algebra, but exceptional double algebra conjecturally rational double algebras. And for type A, which nilpotent element produce exceptional double algebra classified what Kac-Moody, and for other types it was classified recently by Sweet and Katz and Wimberger. So this one might be careful because the rationality of Kac-Moody is slightly different from usual definition. So somewhat the Shizuko-finiteness of of these double algebras are included in the definition of rationality of Kac-Moody. So this result was conjectured by Kac-Moody in principle. But one interesting thing is there are some other important elements which are not listed on the paper of Billy and Katz and Wimberger. I think I have said what I want to say.
Any questions to the speaker?
So suppose k is non-negative integer, so you have r of v lower k. Can you compute the character of this algebra?
You mean it's non-negative integer?
No, just a natural number.
It's a 0.
Sorry?
0.
No, you have r of v lower k, so just C2 algebra. So which is vk modulus.
It's a simple. So R. So this is. So if k is not non-negative integer, this is easy to describe. This is Poisson ideal generated by this.
That's right, but the question is, can you compute the character? So I mean, there is a grading by d on vk by energy, and so this algebra gets a grading from there. So the question is, can you compute the character?
I don't think I can.
But you cannot prove complete reducibility.
So in this category, I can afford type A at least. But there are other modules which are coming from other legal categories. So,
And what's the simplest example? That it is C2 cofinite that doesn't appear in the list? What algebra?
could be, I cannot remember. So
I don't remember. Okay.
Any more questions? Then we have 2 minutes break.